See, I want to tell one important point to you. From third year, first semester onwards, every semester, say third year, first semester, you have one professional elective, one open elective. Second semester, you have two professional electives. Final year, first semester, you have two professional electives, and final year, second semester also, you have two professional electives. From 3-1 onwards, every semester you will be having one open elective. See, open elective is nothing but, so it will be offered by, so you have to select a subject that's not offered by CSC or IT. So it's something like interdisciplinary or intra-domain subjects sort of thing. So you'll be studying some of the EC or electrical or environmental. So whichever subjects you are interested, so we'll be providing you with a list of 4 or 5 electives that we would be offering for your batch. So you have to select one subject among them. See, why I'm telling this point is, say your seniors, now they have to select professional elective. So what we do is, during the flag end of the semester, say when you are in second year, second semester end, before your theory examinations, we'll be circulating a Google form. So you have to select one subject, one option from the options we are providing. See, what is happening is, at the time of writing, you'll write something. Say yesterday what happened was, all the third years they have selected, so now machine learning, IoT, and there's one more option called mobile application development. Among the three, so almost all 90% of the students, they have selected machine learning. So both the sections. So I have offered machine learning for both the sections. See, the other rule is, if there are more than 25 students opted for a particular professional elective, then only we will offer. If there are less than 25, we will not be offering that elective. So using that rule, what we did was, so there were only 7 or 8 students who have opted for IoT, and around 10 students opted for mobile application development. So less than 25 in both the cases. So we have given ML for both the sections. So after drafting the teachers and after finalizing the timetable, everything, see, now today we are supposed to start class for third year and final year, second semester. Now that say again 25 to 30 students, they have called yesterday and they were telling, sir, we want IoT, we want. See, just before, after timetable is finalized, after faculty is fixed. See, again, if you start doing like this, then it becomes very difficult for me and for the department to tackle these issues. See, already I have assigned subjects to all the faculty. So, nick of the moment, say just 1 day before the starting of the semester, if you say we don't want that elective and we want to have some other elective, it becomes very difficult. Even for the faculty also, they should have some preparation time. No? These are all new electives. So just like that, we cannot offer, say if I tell some faculty, they should have some 2-3 days time for preparation at least. So I request all of you, while selecting the option itself, you try to be clear. You take some time, you talk to your seniors, or otherwise, if you are not aware of these electives, you ask me, we'll try to have one introduction, say half an hour if you give. I'll ask all the 3 faculty who are going to take IoT, MAD, and machine learning to tell about the importance of their subject for 10 to 15 minutes. After that, you can decide. But once you decide, so you should take a firm decision and then you should decide and then you should give the option. After giving the option, again, you should not go back. So from next time onwards, if you say, sir, by mistake, say generally many of the girls, what they tell is, yesterday I asked third years, why did you select ML then? Sir, my friend selected ML, but now I'm feeling that ML is tough and IoT. See, ML and IoT, Python 2 units is common in both the subjects. Only 3 units is different. So, depending on, say, the importance of the subject, you please try to select, not depending on which is easy, which is core scoring, all that. Maybe for open electives, you can adopt that strategy, but professional electives, so say if you want to do PG, so which specialization you want to do, depending on that, you should select. Say if you want to go for data science specialization, so machine learning is better. So if you want to go towards system side, say embedded systems, something like that, then IoT is a better option. So if you want to go to pure theoretical science, then this mobile application development is a good option. So depending on which specialization you want to go for, depending on all those things, you have to select your electives. So please remember, so for you also, during this semester, we will be distributing the Google form. So before that, you have a glance at all the professional electives and open electives you are having. So which is better for you. So you discuss with all your friends and then you try to give the option. So once you give the option, then you stick on to that. Don't change it. So did you get my point?
Yes, sir.
36, Nikita. Mute your mic, 36, Nikita. Nikita, 36. Yeah, 21. Unmute your mic. 21, 28, 38. Unmute your mics. See, after your CR is there. Please unmute your mic. CR.
Yes, sir. Good morning, sir.
Yeah, good morning. See, after my class, you please send the absentees list. So you in that absentee list, you include 36, 21. All these numbers you include.
Okay, sir. Yes, sir.
Okay. Okay. So today I'll start second part of the fifth unit. It deals with search trees. So basically, we need to deal with three types of search trees. First, we'll start with binary search tree. Then we will have AVL trees, and then we will have B trees. So B trees are different from binary trees.
Sir?
Yeah.
So actually there was a power cut, sir, so I couldn't respond. Sorry, sir.
So what is your number? 34.
Yes, sir, 34.
Okay. Be attentive. Be attentive. Huh? So if there is power cut, you can use your mobile, no? Huh?
So Wi-Fi, it won't be available for mobile also, sir, when there's power cut.
Wi-Fi, see, you'll have mobile data, no? For sometime 5-10 minutes, you can attend from. Which is important. You can spend 100 rupees a month. Mobile data doesn't cost much, no? So in the case of emergency, you attend classes through your mobile phone.
Okay, sir.
Okay, mute. All of you, please mute your mic. Okay, say B trees, it stands for balanced trees. Okay, balanced trees is different from binary trees. So I'll discuss about B trees at the end. So first, I'll start our discussion with binary search trees. So after that, AVL trees and then B trees. So only binary search trees, we have to write programs. We have to implement programs only for binary search trees. That too for insertion and then search, insertion, search. We don't have delete. I'll discuss delete operation also, but we will not, in the program, we will not implement deletion operation on binary search trees. And then AVL trees and B trees, we will only introduction about these two search trees is there. So we will not write any programs related to AVL trees and B trees. Okay. So let us start with binary search trees. So what is a binary search tree? So binary search tree is a binary tree. What is a binary tree? So a tree in which all the nodes, if they have at most 2 children, or if they satisfy the rule of having at most 2 children, then such type of tree is known as a binary tree. That is, so in a tree, if you restrict a node to have, if you restrict all the nodes to have maximum of 2 children, then such type of trees are known as binary trees. So binary tree, so all the nodes should have maximum of 2 children. All the nodes should have maximum of 2 children. And then apart from this, your binary search tree, apart from being a binary tree, it should also satisfy one more important rule. What is that rule? The value that is stored in the node should be greater than its left child, and the value that is stored in the node should be less than its right child. Okay, so value stored in the node. So this is node, and this is left child, and this is right. So the other rule that your binary search tree, that is all the nodes in, see, whenever I give you a definition in a tree, in a binary tree, so this definition is recursive in nature. So recursive in the sense, so it should be applicable to all the nodes that are there in your binary search tree. So node value, it should be greater than the left. So whatever value you are storing here, so your node value should be greater than its left child, and node value should be less than its right child. So if all the node values, if it satisfies this rule, then such type of a binary tree is known as binary search tree. Okay, did you get my point? So binary search tree is a binary tree. And apart from that, it should also satisfy one more important rule. What is that rule? Value stored in the node should be greater than its left child, and value stored in the node should be less than its right child. Now you try to recollect the heap properties. So we have already discussed about heap. So in the implementation of a priority queue, I think we have used heaps. So can anybody tell how binary search tree is different from a heap? Both are same, or is there any difference? Heap and binary search trees.
So in heap, both left and right should be less than the nodes, sir.
Yeah, good. Yes. So we have discussed about 2 types of heaps. Okay. So max heap and min heap. If you take max heap, for example, node value should be greater than both its children. Whereas here, if you see, node value should be greater than its left child and should be less than its right child. So it is different from heap property. So don't get confused. So heap is different from binary search. Okay. Now let us discuss about the first. So we need to discuss about how to construct a binary tree. So we will use insertion operation for that. Then how to search for a given element in a binary search tree. And then we will also discuss about the deletion operation. Okay, even though so this we will implement it in the program. This also we will implement it in the program. So this I'll discuss only theoretically. We will not implement it programming in the program. So first, let us start with insertion operation. So binary search tree insertion. So let us consider some elements: 45, 15, 79, 90, 10, 55, 12, 20, and then 50. See, you can expect 2 different types of questions in search trees. So first type of question that you can expect in this topic is, they will give a list of numbers like this, and then they'll ask you to construct a binary search tree or an AVL tree or a B tree. So they'll give you a list of numbers like this, and they'll ask you to construct any one of these 3 trees, okay, search trees. Or second type of question that you can expect is, okay, because we have only programmatic implementation only for binary search trees, they may ask you to write a program for implementing insertion search operations on binary search trees. That is directly they may ask you to write a program. That is second type of question. So either they'll give you a set of, or otherwise, the third type of question that you can expect is they may not give you a list of numbers. They'll ask you to explain insertion and deletion operations in binary search tree or AVL tree or B tree. Then please try to remember this set of numbers so that you can explain step by step. You should give explanation and then you should construct a binary search tree or AVL tree or B tree as per the question given. Okay, first let us concentrate on binary search tree. So we'll see how to construct or how to insert node by node into a binary search tree. So binary search tree also, so representation is similar to a binary tree. So binary search trees also can be represented either using arrays or using linked lists. Okay, so linked list means every node in the linked list should have three fields: data field or info field, left pointer which points to the left chain, and right pointer which points to the right chain. So these are the three common fields that will be that the binary search tree will share with binary tree. So binary tree and binary search tree, there is no difference. Only one property is different. What is that property? Node value should be greater than its left child, and node value should be greater than, should be less than its right child. So if any binary tree, if it satisfies this property, then you can call it as a binary search tree. Okay, so representation is similar to your binary tree. Binary search tree and binary tree representation is same. Okay, now if you see how to construct. So first start with 45. So stepwise I'll show you. So for each step you need to provide explanation. So first element you make it as the root. So 45 will become the root of the binary search tree. So consider the second element, 15. So now you tell me 15, is it less than 45? Yes. So the element that you are trying to insert, now your binary search tree has only one element, that to root. Okay, this will become the root. Now second element, so now when you are trying to insert a new element into the binary search tree, so what is the rule that you have to apply? Compare this element with the root element. If it is less, you take the left path direction or left chain direction. If it is greater, you take the right chain direction. So 15 is less than 45. So 45 does not have a left chain. So we have to insert this 15 as the left child of 45. As the left child of 45. So board, is it visible? Do you have any problem? Light, glare?
Visible, sir.
Visible. Okay, thank you. So next, 79. So now your tree has two elements. What is the next element? 79. So 79 compare with 45. 79 is greater than 45. So 79 will be inserted as right child of 45. 79 will be inserted as right child of 40. See, now we have inserted three elements. So from these insertions, now one of the most important point that you can you try to remember is, in a binary search tree, insertions always take place at the leaf level. At the leaf level. So insertions always take place at the leaf level. Now you see 15, it got inserted as the left child of 45. This has become the leaf node. Leaf node means a node with no children is known as a leaf node. So it should not have. So it's if its degree is 0, then it's called as a leaf. So node with no children is known as a leaf. Now if you see 79 also, it got inserted as a leaf. Okay, right child of 40. Next 90. Okay, so this is step 1, step 2. Okay, now 45, 50. This is the existing binary search. 90. Where should I insert 90? So 90 is greater than root. Yes, take the right child direction. 90 is greater than 79. Yes. So if it is greater than, insert 90 as the right child of 70. So once again, if you see, 90 was inserted at the leaf level. So we have inserted this 90 at the leaf level. That is, so whenever you insert a new value, so first what we have to do, you have to create a new node, place this data in the new node info field, then you have to insert node at the correct position. So generally in a binary search tree, new node always gets inserted as the leaf, okay, as the leaf. Please try to remember this. Next, okay, now I'll not show stepwise in the same figure. I'll 10. So 10 is less than 15, 45 is less than 15. So 10 is less than 15? No. It is yes. 10 is less than 15. So it will become the left chain. Okay. So 10 gets inserted as the left chain of 15. Next, 55. So 55 is greater than 45. 55 is less than 79. So now 79 does not have a left chain. So 55 gets inserted as the left chain of 79. As the left chain of 79. Next, 12. 12 is less than 45. 12 is less than 15. 12 is greater than 10. So it will be inserted as right chain of 10. Once again at the leaf level. 20. So 20 is less than 45. 20 is greater than 15. So 15 does not have a right chain. So 20 gets inserted as the right chain of 15. Now 50. 50 is greater than 45. So 50 is less than 79. 50 is less than 55. So 50 gets inserted as left chain of 55. Okay. So I'll just draw it. Once again, I'll draw this. So 45, 15, 79, 10, 20, 55, 90, 50, 12. Now, so this is the final binary search tree that we got after inserting all the elements. So now we have constructed or we have created a binary search tree with how many? 3, 6, 9. So totally 9 elements are given to us. So with these 9 elements, now we have constructed a binary search tree. So this is the final binary search tree. Now, after insertion, let us see how to search for an element in this binary search tree. Let's say, for example, so if the key value given to us is 12. Now you are asked to search for 12. So how should we proceed? So first compare with the root. 12, is it less than 45 or greater than 45? 12 is less than 45. So as per the definition of the binary search tree, if any element is less than the root, so obviously we should have inserted it in the left subtree of the root node. So there is no chance that 12 will appear in the right subtree because right subtree values always will be greater than the root and left subtree values always will be less than the root. So we will take the left subtree direction. So once again, this is the root of the left subtree. So 12 compared with 15. 12, is it less than 15? Yes. So once again, you take this direction. 12, now you compare with 10. 12 is greater than 10. So you come here. When you come here, so this node data matches with 12. So here, search, So your search will become successful. So here, whatever data is stored here, suppose if 12 is the hall ticket number of the student which you are searching for. So here, whatever information is stored against this in this node that you can retrieve and you can return it. Okay, so this is how you have to search for. Okay, I'll take a case. Suppose 51 non-existent data. So 51, is it greater than 45? Yes. 51, is it less than 79? Yes. Come here. 51, is it less than 55? Yes. 51, is it greater than 50? Yes. So actually you have to take the right direction. But if you see 50 does not have a right chain, so this is null. So when during the search, when you come across this null value, then you should say that so 51 is not found in the given binary search tree and your search is unsuccessful. So if you are able to find an element which you are searching for, we say that the search is successful. And when you're able to find, when you have come to a null and you are not able to find the value, then we say that the search is unsuccessful. So please try to remember with one comparison. See, 50, when you are comparing with 51, by just comparing with 45, you are trying to avoid all these values in your comparison. All the values that are less than 45 are straight away removed from your search list. So once again, you are coming here, 51, you are comparing with 79. So you are taking the left side direction. That is, all the values greater than 79 are removed from your search list. So each time we are removing one half of the set. Say if it is less, you are taking the left direction, and all the values in the right chain are right subtree are need not be included, or we are excluding them. So that is how our search continues. Okay, our search continues like that. So now this is about search operation. See, generally, I'll try to compare the performance. I take another typical case. Let us try to construct a binary search tree with this set of values. I take another set of values. I have considered a set of values which are in which order? They are in which order? Decreasing order, or otherwise descending order.
Descending.
Largest to smallest. Okay. Now let us try to construct a binary search. So first insert 90. So 90 will become the root. Next 80. 80 is less than 90. 80 is less than 90. So 80 will become the left child. 70 is less than 90, is less than 80. So 70 we will insert as the left child of 80. 60 is less than 90, less than 80, less than 70. So it will become the left child of 70. Then 50 less than 90, less than 80, less than 70. So 50 will become the left child of 60. Then 40. 40 is less than 90, less than 80, less than 70, less than 60, less than 40. So it will become the left child. So similarly, your 30 will become the left child, 20 and 40. So what is this tree called? It's called as
Left skewed.
leftist or left skewed. So if all the nodes are in the children of, if all the children, if they are oriented in only one direction, either in the left direction or right direction, if they are oriented in the left direction like this, then it's called as a leftist tree or left skewed. If they are oriented in the right direction, so if you consider the values in, so here we have considered in descending order. If you consider the values in ascending order, 10 to 90, if you consider, and if you construct a tree, now your tree will become like this: 10, 20, 30, 40, 50, 60, 70, 80, 90. So it results in a right skew tree or rightist tree. So if you consider the values from 10, 20 up to 90 like this, and if you construct a binary search tree, now you get a rightist or right skew tree. Now leftist or rightist trees, so they'll become worst case examples for your binary search. See, so once again you try to recollect the definition of complete binary tree. So complete binary tree is if all the nodes, if they are numbered, say numbering scheme is n, 2n, what is about how we have numbered. If you are starting from 0, how we have to give numbers for the nodes in a binary tree. If we are starting from 0, suppose it is 0, then 2n plus 1 and 2n plus 2. So if any node, if it is numbered as n, its left child should be numbered as 2n plus 1 and right child should be numbered as 2n plus 2. So if it is, if you are starting the root from 1, then it should be 2n plus 1. Okay, don't worry about that. So using this scheme, you have to give numbers to all the nodes. And if these numbers are continuous, then such type of a binary tree is known as a complete binary tree. That is how we have defined the complete binary tree. So if a complete binary tree, say for example, we have constructed a binary search tree with a given set of elements, and if your tree is like this, so this is a full binary tree. Or if your tree happens to be a complete binary tree. So this is an example of a complete binary tree. This is a full binary tree and this is a complete. Whether it is full or complete binary tree, so the maximum number of comparisons that you would be requiring is only log n. If there are n number of elements, with n number of elements, if you have constructed a binary search tree, and if that binary search tree happens to be a full binary tree or complete binary tree, the maximum height of a full binary tree or complete binary tree generally will be restricted to log n base 2. So that is why. So for example, if I am searching for element which is total 1, 2, 3 maximum. So totally how many elements are there? 1, 2, 3, 4, 5, 6, 7. So it is log of 7 or log of 8 is okay. This is approximately 3. With maximum 3 comparisons, you can tell whether that element is there or not. So if it results in, after constructing a binary search tree, if it results in a full binary tree or complete binary tree, so this is best case time complex. Best case is big O of log. On the other hand, if it results in a skewed tree like this, which represents the worst case, now this big O of n. So it has become a linear search. Now you see, if I am searching for 10 in this binary search tree, I'll start from here. 10 compare with 90, 10 is less than 90. Second element, third element, fourth, fifth, sixth, seventh, eighth, ninth comparison. So totally there are 9 elements and you require 9 comparisons to tell that this element is present in the binary search. This is nothing but equal to n comparison. There are n elements and you took n comparison. So luckily, after constructing the binary search tree, if the binary search tree, if the height is restricted to log n, in the best case, so with only n, log n number of comparisons, we'll be able to tell whether an element is present in the binary tree or not. In the worst case, say if your binary search tree happens to be a skewed or a leftist or rightist tree, then you may require maximum of big O of n comparisons to tell whether an element is present or not. Okay, don't worry much about this. So worst case time complexity for searching an element in the binary search tree is big O of n. So generally worst case is skewed tree for binary search tree. And best case is if the binary search tree that's constructed, if it happens to be a full binary tree or complete binary tree, in the best case, so you may require only log n number of comparisons. Okay, but you don't know after constructing with a given set of elements, if you construct a binary search tree, it may result in a complete binary tree or it may result in a skewed tree. We don't know. We are not restricting the height. So in the next topic, which I'm calling as ABL trees. ABL tree is also a binary search tree, but there we are restricting the height of the binary tree to log n. So such type of trees are known as balanced trees. When I discuss ABL tree, I'll discuss more about it. Just here you try to remember. So binary search tree may be height balanced or it may not be height balanced. So this is, if it is a complete binary tree or a full binary tree, it is height balanced. Height balanced means what do you mean by a height balanced binary tree? Already we have discussed. So if you restrict the height of a, suppose with n number of nodes, if you are constructing a binary tree, and if you restrict the height of the binary tree to log n, then it's called as a height balanced binary tree. If you restrict the height of the balanced tree to log n, then it's called as a height balanced binary tree. So height balanced binary trees will have maximum of log n as their height. Okay, so this represents the best case. So if you construct a binary search tree with the log n height, maximum number of comparisons that you would be requiring for searching an element will go of log n. And in the case of if it is not a height balanced binary tree, suppose if the constructed tree happens to be a skewed tree like this or like this, then you may require log n number, big O of n number of comparisons. So that's what you have to remember. Worst case is big O of n, and best case or average case is big O of log n. So this is about the search operation. So insertion and search are discussed. Yes, any doubts? So last week in your lab, which programs you have tried? Which programs you have completed? Do you have any programs to do in this lab session, today's lab session?
Sorting, sir. In the last week, we have completed all the sorting programs.
So you have graph programs, no?
Sir?
This week you can do graph programs, no?
Yes, sir. Even ma'am informed, sir, like this time we have to do DFS and BFS.
Okay.
Yes, sir.
So why I'm asking this question is, so if you don't have a program, then I'll write program. Otherwise, I want to explain a deletion operation. So in tomorrow's class, I'll write the program. Okay, better. Let us start with the program. I'll explain deletion operation after this. So in the program, we will be writing only for the implementation of insert function, search function, and then traversal. So already we wrote in order, pre-order, and post-order recursive tree traversals. Same traversals we'll also add for binary search tree. Okay. So tomorrow, if I forget at the time of explaining the deletion function, I'll try to also discuss about the applications of search trees. So binary search trees basically are used for two purposes. One is search. The name itself suggests you can use them for searching operation, and then the other important application is you can also use them for sorting. So in the next class, I'll explain how to use binary search trees for sorting. Okay, just write down the program. So first, definition of binary search tree implementation. So as usual, you have to define the So this is the definition of the node structure. So it is similar to your, so almost all this program, binary search tree program is almost all similar to your binary tree program. Okay. So after this class definition, so one constructor is required. So we will define the constructor outside the class. Okay, right. So all the member functions. So let us, so I'll use only public. Otherwise, you will have some problem with this. Okay, what are the functions? Void, insert, node, so I'm passing two pointers. First one is a pointer to the root node, and second one is pointer to the newly created. So insert should take the root node address and newly created node's address and this newly created node should be inserted into the binary search tree to which this root node is pointing to. I'll explain when I write that insert function. So now void, so as usual, pre-order. So let us start with pre-order. So it takes root node and then root node address and then traverses this PST pointed to by this root node in pre-order and then displays all the values stored in the all the nodes in pre-order. So similarly, void in order, same thing. Void post order. So this is similar to a binary tree. So when you call pre-order, it displays all the node values in pre-order. This will display in unorder, this will display in post order. What is the other function? Search function. Void search. You should take two values. BT node, that is root node's address, and then an integer, key value. So now what it should do? It should take key value, it should search whether this key value exists in the binary search tree pointed to by this root node. If it is present in any node, that node's address should be written. Sorry, here we should write node's address. So it should return that node's address. BT node star. So if the element is not found, then it will return a null value. Okay. The end of the class definition. So we are defining the class with, so how many? 1, 2, 3, 4, 5 functions and 1 constructor. So this is for inserting a new node into an already existing binary search tree. This will perform pre-order traversal on the given binary search tree and then displays the elements in pre-order or in pre-order. Then this will traverse all the nodes in the binary search tree in order and then display the values. Post order, it will traverse the given binary search tree in post order and then display all the elements. And searches, it takes a key value and searches whether this element exists in the binary search tree or not. If it exists, then the node in which this value is stored, that node's address will be. Yeah. Any doubts? Now let us define each of these functions. So if you have any doubts, you please ask. So I'm not adding delete function in this. We don't have programmatic implementation. So I'll explain theoretically delete function. Yes, somebody was asking about. Name of the class is EST. Writing this side is becoming difficult for me. I'll write on the right side. Okay. So first, what is that? Constructor, no? So name of the class is EST. So I have not used the templates. So if I use templates again, so you know, so trees programs itself is difficult. If I use templates, so it will become more difficult. So in order to make programs easy, I'm not using templates. So if you want to use templates, so you have to use template for the structure definition. Instead of integer info, you can take it as capital T. So you have to define. So template class T and then make that the info data type as generic data. What is the name of the constructor? Same. So simple, only one statement, initialize root to. So whenever you are working with binary trees, you have to always initialize the root to null. That's what I am doing in this constructor. Okay. Then what is the first function? Insert function. Void inst. What is the name of the function? Insert. So how many parameters does it take? 2 parameters. So One is BT node. NN stands for new node. Okay. Still 45 minutes, I think. Okay, no problem. First, if root is equal to null, is it visible? So I want a lot of
Please
space.
increase the font a bit, sir.
Not able to see?
Somewhat font increase, sir, please.
Yeah. Increase. So if root is equal to null, root is equal to new node, root node added return. Okay. If one minute, you just try it. Already we have used root as the one variable. No? It's better you use some other name. So it will. So already we have declared root as the global variable. No? So better to use some other name. So you name it as BT node 3. So this root would be pointing to the root node. It will hold the root node's address. So if 3 info, I'll share the program. If 3 info is equal to new node info cout duplicate, and then we say return. If 3 info is greater than new node info greater than new node info, if 3 left node added to left and return. End of else. This time 49. Okay, else if so this is greater than only one. It is greater than if it is equal to duplicate. If it is greater than, if it is less than, we will come here. That is less. So I think that this is enough. Yes. If key right is not equal to null, same thing. Insert key right and then n. Else, this is for this piece. Same thing. Key right equal to n1. Here left, here right. See out node added to right. Node added to right. And then return the end of this else and the end of this else. This is end of this and this is end of this. And finally, end of insert function. What do you have after this class? Third hour?
Library hour, sir. It's free.
Okay. Just five minutes, I think. I require 5 minutes. Otherwise, tomorrow again I have to write. Okay.
Okay, sir.
Now let us see some cases. First, assume that root is null. So root is initialized to null. Null in the sense it is an empty binary search string. Let us consider the same values. Okay. 45, 15. I'll just take first 5 values. 79, 90. After that, what is the next value? 10. Okay. First 5 values we will see. So in the main function, what we would be doing is we would be creating a new node. So first 45. So 45 will keep it in the info field. Both left and right links we will make it as null, and NN will be made to pointers. Okay. So first step is, so initially we assume that the binary search tree is empty. Now you see. Root equal to null, yes, this condition is true. It means that initially your binary search tree is empty. So now if it is empty, what we have to do? The node, whatever we have created, that itself we have to make it as the root node. You see, root equal to null, yes. NN we are assigning to root. So suppose if NN, if this node's address is 50H, NN value would be 50H. This, so root we are assigning 50H, that is that is, now if you see NN when you assign to root, now what is the status? So this will become like this. So now 45 will be green. So your root would be pointing to this. Okay, so return. So the control will go back to the calling function, that is main function. So main first, if you say 45 is the value that you want to insert, so it will be inserted as the root. Next, once again, I want to insert 15. So how you have to insert? So I'll give 15 and root node's address. So first, a new node will be created. So we will insert this data. Both links we will make, and NN will be made to point. Now you see. So once again, So your tree would be pointing to this root node, and this NN would be pointing to this newly created node. So these are the two parameters. Root equal to null. Is root equal to null? No. We will come here. Tree info is equal to NN info. 45 is equal to 15? No. So why we are considering this condition is generally in any search tree, our search trees does not allow two nodes to have the same key values. So for example, if one node is having key value 45, we should not insert another node with same key value 45. So duplicate value should not be allowed. Say instead of 15, if I give 45 here, so what happens? 45 equal to 45? Yes. So duplicate and return. So it will not allow duplicate value to be inserted. So that also we should take it. The next condition is, so now you come here, tree info. What is tree info? Tree is pointing to root. So this is 45 and NN info is 15. Am I right? 45 is greater than 15? Yes. So root node value is greater than newly the node to be inserted value? Yes. 45 is greater than 15? Yes. So if this is the case, where should I insert 15? As the left child of root. That's what we are doing. Now you see, then we are checking tree left is equal to null. So tree is pointing to this node. Is tree left null? Yes. Tree left is null. If that is the case, if it is not null, you have to continue your search until you find the left child as null. Is not equal to null? No, we will come to else case. So else case means the left child or left pointer is null. So NN, I am attaching it as tree of left. Suppose if this node's address is 50H, so I am storing 50H here. So if you store 50H, that is NN we are storing in the tree left pointer here, that is left pointer of this root node. Now we point to newly created and we are displaying a message node added to left. So this node we have added to as the left child. So finally after this, now root 45. So this is the new node structure. Sorry, new binary search tree structure. So once again, so 79. So what happens? A new node will be created. 79. So your tree would be pointing to this. Come here. Root equal to null? No. Tree info is equal to NN info. 45 is equal to 79? No. So we will come here. So what is tree info 45? What is new node info 79? 45 is greater than 79? No. So this is, for this is, where is the else here? We will come to this else. Now you see, tree right. What is tree right? Tree is pointing to this null. Tree right is null. So tree right is not equal to null condition becomes false. So you come here. So we are assigning new node as the right child of tree. So suppose if this node's address is 75H, we are storing here, that is right node. So after this, so what happens? Now you see, we are displaying node added right and then return. So after all this, new tree looks like this. So 45. Left chain will be 15 and right chain will be 7. So chain links would be none. Both left and right links would be none. Now let us consider one more. So this is root. I'm creating one more. So what is that? 90. So new node will point to this, both links null. So when you pass root as the parameter, so 3 is the name of the formal parameter. So 3 now will point to the same root. Okay, now you tell me, so 3 is pointing to this. So now I want to insert 90. You see, what is root equal to null? Root is not equal to null. So we will come here. Tree info. What is tree info? 45. NN info 90. 45 is equal to 90. No. We will come here. Okay. So now we are using recursive call. Be careful. Try to follow carefully. Tree info. What is tree info? 45. What is NN info? 9. 45 is greater than 90? False. So we come to else case. Now you see, tree right. What is tree right? So 3 is pointing to this root node. Does it have a right chain? Yes. 3 right. Now you see, 3 right is not equal to null? Yes. This condition is true. When this condition is true, now you see, we are recursively calling the same insert function. With what are the parameters? With its right chain and NN. Now, the right chain of the root is pointing, 3 is pointing to this. Now, when you call it 3 right, so this is 3. 3 right now will become 3. So 3 right will be copied into. So that is with this node, once again we have gone. So your 3 now will be pointing to this 70. Now let us trace. So root equal to null, root is not equal to null. 3 info, what is 3 info? 79. So 79 equal to 90? No. So we will come to this case. What is 3 info? 79. 79 is greater than 90? False. We will come here. So what is this? 3 right is not equal to null. So 3 is pointing to this node. 3 right is not equal to null condition. So this becomes false. So we will come to else case. Now you see, NN, we are attaching it as 3. So suppose if this node's address is 100H, we are storing it here. For this node, this will become the right chain. So after all this, so for 45, 15 will become the right chain, 79 and 90 will become the right chain. So this is recursive call. Okay, this and this we try to follow carefully. So where we have to insert. So if it is greater, we are taking the right chain direction. If it is less, we are taking the left chain direction. So recursively from here, we will go here, we will go. Suppose if I want to insert 100, so 3 right, so we'll come here, we'll come here. So 900 will be inserted. Like that, we will insert. So just try to follow the code. So we are just comparing the element. So if the root is null, first node will be added as the root node. Only first time this condition will become true, otherwise it will become false. Then we are checking the element that we are trying to insert already is present. If it is already present, then we say duplicate and will not insert the element because it's already there. So if it is greater, okay. So if the element that you are trying to insert, if it is greater, we take this direction. So we'll check whether the node has right child or not. If it does not have a right child, straight away the new node will be inserted as the right child. If it has a right child, then again we are passing that right child as the parameter. So next time again that right child will become the node current node. So again you have to check whether that has a right child or not. If it does not have a right child, straight away you can insert. Otherwise, you have to move towards its right child. Like that, recursively we will be. So this is the code for insert function. So tomorrow I'll continue. You take break and then afternoon we'll have lab. No? So you can join the lab. So 50, earlier 57 students were there. Now 56 students. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Okay.